All right, good morning, everyone. Presumably, before we get started, do people have questions? Okay, so our hope is to get out homework 3 in the next day or two. So watch for that. We'll post to Piazza. Also, apologies that last lecture took so long to appear on Canvas for you. It also took that long for it to appear anywhere for us. The recording must be somewhat backlogged, presumably due to just really heavy Zoom usage. But it should be there now, and let us know if you see anything like that again. And we apologize for that. We're not entirely sure what was going on with that. Right. Okay. So one of the things that was correctly brought to our attention about the latest homework was that there was a question which asked students to use a fairly regularly used data set for an introduction to machine learning class, which asks that some statistical analysis be done as a function of various data about different neighborhoods, and specifically looking at various possibilities for doing analysis and prediction of certain types of crime and crime statistics in those neighborhoods. Okay, and I want to briefly describe some of the concerns that rightly ought to come up when thinking about using machine learning in this way, and mention that towards the end of class, the end of this term, we're hoping to give a more lengthy explanation of some of the concerns that might come up when using machine learning for prediction tasks such as these, although these problems are much more widespread than simply thinking about using machine learning technology when thinking about statistics related to crime. Okay. And please feel free to jump in. Just in general, that's always something that we encourage, but in particular, this part of this lecture is meant to be more provocative than solution oriented. So I'm not trying to go to one particular answer. I'm sort of reminding you to always do this kind of thinking when developing machine learning systems, and deciding whether or not one ought to develop a machine learning system for certain kinds of tasks, and also whether a particular data set is appropriate for doing that sort of task, even if you believe that task is reasonable to do. Okay? So far in this class, we've talked a little bit about the following question, right? Is it possible to predict y from x, right? And we haven't really said much about what y and x are, other than giving some sort of cutesy examples, and on the homework's giving you some slightly more realistic data sets. And it's pretty common in computer science to try to abstract away any details that are not relevant to the mathematical problem at hand. And as some of the posts on the Piazza board for this particular problem did, it was the case that some people found it easy to sort of think, we're going to try to predict y from x. I'm ignoring what y and x are, right? This is just like a mathematical question, right? However, that's like a relatively unnuanced view of machine learning, right? And in general, if we want our systems to work well, we have to actually understand something about the domain we're trying to do prediction within, right? Nevertheless, right, you can certainly ask the following questions for any kind of machine learning task you might be trying to accomplish. Right? Is it possible to predict y from x? And furthermore, what kinds of interventions, perhaps on X, perhaps on other things, are appropriate for changing Y, right? Yeah. And if we can do either, what are the right measures of effectiveness, right? So we've talked about various loss functions, right? And loss functions are some way to think about how well we're doing at a particular prediction task, right? We won't talk as much about sort of the right measures of effectiveness for changing Y based on certain kinds of interventions. If you're interested in that, there are other courses that have to do with causality that are available also in CSE, and we can tell you a little bit more about those. But broadly speaking, machine learning often asks, is it possible to predict Y from X? Is it possible to change Y based on some behavioral change or some kind of sort of outside external force affecting something else in the system to change the values of Y we see? And then there's an interesting question about sort of how well we're doing predicting Y from X, or how well we are changing Y based on these particular interventions we might be considering. Right? And standard machine learning might just ignore that we've instantiated crime for Y and various specific features for X, and not think about the social implications or some kind of other important implications for that. Right? And that's not a great view of any problem. You'll do a better job with some domain knowledge in any kind of context. But in particular, when we're thinking about criminal statistics, this is a much thornier issue than simply thinking about predicting Y from X and ignoring what X is and not being concerned about sort of the implications of what might be done with such a tool, right? And I want you to think about the following questions, and jump in if you have any comments about any of these. But it might be the case that we can do a reasonably good job at our prediction task, whatever loss function we were talking about, while simultaneously having some of these other concerns, right? So what if it's the case that we're doing a reasonably good job with our prediction task according to our loss function, but our predictions are only doing a good job predicting certain kinds of crimes? For example, maybe they're doing a really good job with property crimes, but they're not doing as good of a job predicting where violent crimes are taking place, for example, right? This may be somewhat of an issue with the definition of loss that we considered, but for that reason, since we as machine learning experts are actually the people who are writing down the loss functions we're optimizing, it's actually really critical that we understand what the various values of Y we're considering are, right? And that they are not 0, 1 loss, or the analogs for multi-class learning is very rarely the thing you actually want to optimize. It's presumably much more important to predict certain kinds of crime than others. And doing a really great job predicting what kinds of bicycles are going to be stolen, where bicycles are going to be stolen in Seattle, is presumably somewhat less important than predicting other types of crime. Furthermore, if you totally ignore what Y and X are, you might not recognize that whatever system you've set up, whatever model you've trained, it might be the case that it's only finding crime in certain neighborhoods. That the errors will almost certainly not be distributed, or sort of the goodness of the predictions will almost certainly not be distributed evenly across the range of places you're considering, right? And within the United States, our neighborhoods affect so much about our lives, right? It's not the case that neighborhoods sort of have a uniform distribution of people due to socioeconomic class and education and race. That's certainly not the case. right? And so if we're doing a better job at prediction, or we are making more predictions for certain types of crimes in certain neighborhoods, that's going to strongly correlate with those things having strong correlation with race and class. And that can be very problematic for a whole slew of reasons, which we probably won't talk much more about, at least in this very condensed version where we're talking about some of these concerns. But that's definitely something to keep in mind. Furthermore, and at least those two things these are at least somewhat a function of maybe our loss function didn't accurately capture exactly what we wanted. It was somewhat misspecified, right? That might be one of the reasons that we might be having these sorts of problems. But it may also be the case that we have a difference in opinions in terms of what we think are acceptable features to use to predict crime, right? So as I mentioned a moment ago, different neighborhoods have really different demographic data corresponding to the people who live there or work there. And while those things are correlated, they may or may not be causal, right? But it's almost certainly the case that if you gather more features, right, and do, the more features you gather about different neighborhoods, the lower you're going to be able to drive your loss, whatever your loss is, when doing some kind of simple model selection and looking at your training error with respect to those features, right? But that's entirely ignoring whether or not we consider certain features acceptable for use when doing certain kinds of prediction tasks, right? So if you are an individual who is in a courtroom, for example, right, there are certain kinds of permissible evidence, right? And there are certain things which, if they were, they wouldn't be allowed to be admitted into evidence when deciding whether or not you belonged, you had possibly committed a crime, right? And at least in machine learning, right, or in this class so far, we haven't really talked about sort of what features we consider socially or otherwise acceptable in using to make some kind of prediction. And in general, right, if you add more features, you'll be able to do a slightly better job in terms of prediction, assuming you have enough data to actually use those in a meaningful way. But that's really problematic if, we're thinking about features including demographic information, right, such as race, gender, class, or other salient information which may involve protected classes, right? If these belong to the set of features X from which we are trying to discern some frequency of certain kinds of criminal statistics, that can really have different implications here than if X are simply expression patterns of certain kinds of genes, and Y is, the probability that someone develops skin cancer, right? It's really important that there be an open conversation about sort of what features we consider acceptable to use when making certain kinds of predictions. And I'm not saying that these are features that we necessarily want or do not want to use in the prediction task. It's just critical that we understand what the implications of making those decisions may be. Furthermore, we sort of have, for virtually all of the class, assumed that our data was generated in a super nice way, right? That XY pairs in our data set were drawn IID from some nice distribution, and that we actually cared about our performance of the model we trained on that IID drawn training data for future draws from that same distribution, right? And that is almost never the actual setting. That's an idealized setting that we very, very rarely see in practice. And that's particularly problematic if the gathering process sort of has baked into it inherent biases for different populations. You know, for example, and some of this comes to the fore when thinking that like we're sort of misspecifying labels, right? So if one is thinking about the number of police reports or the number of times 911 was called for incidents in certain neighborhoods, those are not equivalent numbers to the number of crimes committed in certain neighborhoods, right? Different neighborhoods have really different rates of crime reporting. They have very different rates at which different crimes are actually observed by the police, are charged by the police, that they involve either arrests or convictions. All of those things end up being quite different, right? So if what you have is a list of arrests or a list of convictions, and you're using that list as a proxy for a list of where crimes were committed or particular crimes were committed, you have an incomplete set. And moreover, you probably don't have a set which is sort of nicely distributed according to where crimes actually were committed, right? There will be certain neighborhoods which are very over or underrepresented in that list, right? So, you know, in general, the fact that our data is generally not IID, if it's generated by humans who are doing the collection process, who aren't sort of trained in statistics, right? And weren't developing this data set for statistical analysis, but were instead, you know, doing some task that they were asked to do, that is almost certainly not going to be an IID data set, and it's going to have additional concerns that come to the fore if using that data set to make predictions. Furthermore, it's important that we actually think about not just like how well our model is doing at predicting a particular thing, but that we ask what's going to be done with these predictions, right? And all of these things were sort of vaguely alluded to at the end of this problem on your homework, right? But this idea that once you have some understanding of the model that relates X to Y, what's going to actually be done with that, right? Are we going to actually ask people over the age of 65 to move into neighborhoods that have higher crime rates according to our analysis? We can say absolutely nothing about what that's going to do, first of all. But second of all, it's really important that we understand why someone wants to understand the relationship between X and Y and what actions are going to be taken as a result of whatever model we're going to be developing. So we can develop a better model for them, but also so we can determine whether or not the possible interventions they're considering are appropriate, ethical, and perhaps useful. Okay, so one might ask whether most of these concerns, also for some reason my slides are not, there we go. Okay, apologies, somehow there's some lag here. I'm not sure what that is. Okay, so my next slide, while I fix that, asks whether most of these concerns or all of these concerns might be mitigated by simply removing demographic information from the data set we're considering, right? So the data set in your homework contained a number of different pieces of demographic, at least population level demographic information, right? And that can be somewhat concerning, right? If you're trying to build some model to understand crime statistics or any kind of statistic really, and you're trying to understand how that may correlate with demographics, that brings up some concern that your model may make different predictions or you may be able to draw different conclusions for people or neighborhoods with different demographics. Right? You're certainly allowing for that possibility by providing that information to your training And one possible, sort of the first thing you might attempt if you hadn't thought about this very long, or if you're not a social scientist, you might, or if you're not a machine learning expert, right? This is like the standard thing that people generally propose when hearing that, some algorithm has some behavior that's correlated with race or with gender. The first proposal is to simply remove those features from a data set. And unfortunately, this often places us in the worst of all worlds, right? If you remove demographic information from a data set where you actually care about the predictions you're making, doing so simultaneously makes it difficult, if not impossible, for you to determine whether your predictions are correlated with that demographic information, right? And it doesn't actually remove the possibility that your predictions are correlated with race or gender, right? So a great example, the reason for this is that like many of our features that we're generally considering have correlation amongst them, right? We've been talking about neighborhoods and how they correlate with demographic information in a very loose way, right? But if, for example, what I have is the block number for different crimes in the city of Seattle, and I've ignored demographic information, right? If that's all I have the number of crimes that were committed on each block in the city of Seattle. Unfortunately, which block we are considering has strong correlation with the demographics of the neighborhood it belongs to, right? So simply removing that information from a data set and then doing prediction won't guarantee that the predictions we're doing do not have strong correlation with the demographic information that we've removed. So for that reason, we generally, as machine learning experts should know that simply erasing certain features won't mean that our predictions will be uncorrelated with those features. This is primarily a concern when we're talking about criminal prediction for a bunch of reasons, right? And we won't talk too much more about it today, simply because we are primarily trying to teach you in this course a bunch of technical tools, but we're teaching you those technical tools with the hope that you'll understand that they only work well if you think very carefully about whether the assumptions we've talked about at the beginning are satisfied, and furthermore, think about the possible implications when they're not. So identically distributed data is a really great example, right? And we have sort of alluded to, lots of people have asked questions that have tried to get at whether our features are strongly correlated with one another, right? When we're talking about various linear models, when we're talking about sort of having features which are perfectly correlated, that often comes up when thinking about whether or not certain matrices are invertible, right? Whether things are of full rank or of nearly full rank, or many of the technical tools we've been developing in the course so far have been aiming to get you to think about some of the technical considerations that come into developing machine learning algorithms. And these tools are incredibly useful when trying to understand how to develop machine learning systems in more nuanced environments, right? There are additional concerns you need to take into account when you're thinking about these sorts of settings. And we are not condoning or suggesting that you ought to use machine learning systems to do this or any other kind of prediction task, right? You certainly need to know more about a data set than we have provided you about this one or any other ones in the homework to determine whether you're actually doing some useful prediction task that is worthy of deployment, right? So we may talk about this a little bit more towards the end of the term, but the primary takeaway from this monologue of mine is that we can certainly do statistical analysis of data sets that have to do with crime in the United States, we should be incredibly careful to when interpreting or drawing conclusions from any of the statistical analyses we've done on those data sets, right? There are many, many nuanced, important, and complicated issues that come up when using statistical analysis for these sorts of things, especially because the data sets are often generated in some way that has such strong correlation with race or gender or class. That being said, this is still, you would be surprised how many of you may end up working for a company who at some point or other has developed a system to aid in certain kinds of criminal prediction tasks, for better or worse, right? So it's important for you to have grappled with this somewhat a little bit even now, right? You'll all have internships at large tech companies, and you will regularly be asked to do things which you could certainly sort of put on your I'm trying to predict Y from X hat and ignore what Y and X are, right? But it's important that you actually think a little bit about what you're doing, whether the technical assumptions that we generally make are satisfied, and if not, what the implications might be for the conclusions you might draw, and whether or not our technical assumptions are satisfied, sort of what the implications might be for making models that describe the relationship between X and Y for different environments. Okay. So I want to leave a couple of minutes here, or I want to encourage anyone to bring up any comments they may have about this. I gave a very brief and very incomplete description of some thoughts I had, and that is, one could write several books or many books about this, right? So this is far from a complete description of some of the issues that arise here. But I'd like to open it up for a couple minutes for people to comment or ask questions.
I guess I have kind of a question about, like, no matter how good a prediction system is, there's always some false positive rate, even if it's very small. And a lot of these systems for like predicting things about a crime or like health, like predicting a disease, if you, like, I think we had a homework problem, right? If you apply something at random, and the thing is where, like someone being a criminal or having a disease. And even if it's like 99% accurate, you go and give that to like 1,000 random people, and if only 1% of them has the problem or is a criminal, that means like, I don't know, half, if someone tests positive or, gets flagged as a criminal, then there's only a 50% chance there really are. And that's actually for something that's not that rare, like 1%, right? And like, and if you broadly target a whole population, right, with like a lot of things, you're just, it's so easy to profile a person in, when you have their data, right? Like things are being applied to everybody. But like you never see commercial systems or like people talking about a false positive rate at all, right? It's not something anyone ever says.
So right. So Denise is making a great point, right? That 0-1 loss is not a great description for what we might actually care about, right? So if we have a very different rate of positive and negative examples, what we might care about is something having to do with false positive and false negative rate, which is not sort of just the average of those two values, right? And that's definitely something that comes into play here, right? And in fact, it's sort of codified in much of the US legal code that it's better for 10 guilty people to go free than 1 innocent person to be placed in prison wrongly. So there has been both technical and non-technical treatment of thinking about false positives and false negatives in the context of thinking about crime prediction or various other things. And that's definitely something to consider, right? So false positives are inevitable if you're doing prediction, unless you label everyone as negative, in which case you're not doing any kind of meaningful prediction. So thinking about whether you actually just care about 0-1 loss, or whether you care about some more nuanced relationship between false positives and false negatives is something that's really important here. And I would push back a little bit and say that false positive and false negative rate is something that is talked about a little bit, both for commercial systems and for, we're living in a world where we have some very interesting machine learning prediction problems that are new to us in terms of like what we're trying to predict precisely, but old to us in terms of when doing prediction for new diseases, for example, right? One of the things we're often thinking about is like, how do we design a test for a certain kind of disease or for the antibodies for that kind of disease? And actually, if you've read even like a brief description in like the Seattle Times or the New York Times, many of those tests, they're talking not just about their accuracy, they are talking about specificity, right? So they're talking actually here about like the false positive rate of these certain kinds of tests, right? Because those are important. And even just sort of commercial news coverage of these things have thus far, I think, actually been doing a shockingly good job describing that we don't just want high accuracy, we want to have relatively few false positives and also relatively few false negatives, right? That it's important that we do a good job predicting people who actually have the disease, and the people who don't do not. And in the case of various tools that have to do with criminal justice, I guess it depends on what kind of thing you're talking about, but like there's definitely a discussion amongst a variety of people about false positive and false negative rates of these things as well.
Right. I guess I just mean that even when people are told, oh, this test is 99% specific, or this system only makes, they're never told that, oh, well, that means if you run this test on a random person and they test positive, you're never, like, the paper never says that, oh, well, actually, if you took this test and you tested positive, that really only means you have a 20% chance of having the condition. Or if you, pull over a random person and like run this prediction thing, and they're, sometimes it's almost meaningless, like facial recognition surveillance or something. If you surveil everybody, you're just going to find a lot of false positives all over the place. If you actually pointed at everybody, I don't know. That's like, it's just not explained.
Right. And I think this brings up the point that we have a lot more work to do when explaining things to the public, making sure we're using language and descriptions that are actually available to people who maybe don't have PhDs in machine learning or statistics, right? People with high school education should be perfectly capable of understanding this issue we're currently talking about, right? And we just need to pitch it in the appropriate way. And that's important. I do want to make some small pivot and say, the issues that arise here are not simply issues of accuracy, right? Even if we had a perfectly accurate predictor, the questions of what features we consider appropriate to use to do prediction are still meaningful, and whether or not we want to do that prediction, even if we could do a perfectly good job, are still really important questions, right? So part of the story is understanding how errors are distributed, but that's far from everything. Okay, so I want to give us like 2 more minutes, and then I'm happy to stay after class and turn off the recording button and allow people to have more of a discussion if they want. So I'll give people another couple minutes to make comments or ask questions.
I feel like I should. Oh no, I'm sorry. Someone else should go.
No, go for it. Mine was going to be a technical question, so don't go for it.
Okay, I feel like I should say something. I wrote the thing in the Piazza post, and I guess something that I feel really confused by and also hurt by is like, I totally agree that these are important questions to ask and consider. But I guess like, especially like in the workflow of the problem, we were not guided to like look at the features and consider them and then think, is this a model that we want to make? What are the potential implications of that? Like all the things that you're suggesting would be like good points of logic to go through. We did not go through them. We were asked to like make it and then later asked to be like, could this be hurtful? And I think that that's really upsetting to me. And that's really like, I feel like I've kind of been duped. You know what I mean? Like, I feel like I was asked to do a hurtful thing and then told like, oh, by the way, this can have really violent consequences. But like, I think if we're meant to be like educated in how to make these decisions, we need to be educated in how to make the decisions. You know what I mean? It feels like, it feels like we were not guided.
Yeah. So I think that's a valid set of thoughts and emotions, and I think we're going to work on developing a better way to sort of guide people through this. Valid. That's certainly valid, right? Somewhat unfortunately, based on the way that people in tech are generally asked to solve problems, right? They're generally provided a data set and asked to do these things, and then, you know, sort of after the fact asked, oh, what if we did this? What would this model say that would mean, right? And this is, you know, the construction of this problem is largely reflective of the way that we are generally expected to solve problems, but I agree it's not the right one in many contexts. So we'll think more carefully about that.
And I'll save my question for after class. It's cool.
Okay. Kevin, are you unmuted for some reason?
I wasn't unmuted.
Sorry, it looked like you were in my description.
But yeah, that problem was written. I'll just echo a lot of what you said. Thank you for the excellent lecture. Typically, we have to answer for our models once they're already made and people are trying to interpret them incorrectly. And typically, we always plan to have a lecture on some of the more ethical and fairness issues in machine learning, of supervised learning in particular, towards the end of the course. But I think that the fact that the reaction this problem got, I think, has really motivated at least me to rethink where we should place that lecture in the context of this class. Because obviously, if we're bringing up these kind of questions and concerns, we shouldn't be addressing them only after you've gone through the problem. And so I think we will address later in the quarter, assuming we have time in the lecture schedule, we will be addressing some of these issues from even a more technical standpoint, and like actual, we've had a great conversation here about how to look at your features, how to think about it, and what's actually valid to use in your model, and thinking about these different features. But there are also imperfect technical tools to correct for some of these kinds of things, or to at least get you thinking about the next level of like, okay, this is the data I have. Should I ignore this feature? Or should I actually be aware of this feature and correct for the use of it so I'm not unfairly biasing myself using it? And so I'm looking forward to giving that lecture. But I really regret not having that sooner.
Okay, so thank you all for bearing with us and having that conversation. And I definitely would encourage anyone who would like to stay around after class once we've turned off the recording, in case that has changed anyone's behavior. I'm happy to talk more about these things after class. Okay, so not to be abrupt when describing, one consideration and moving on to sort of more standard, regularly scheduled programming. However, we have 80 minutes in this class, and we are trying to give you enough technical tools that you could even ask sort of these questions that are both technical and non-technical in nature about machine learning systems and prediction. So as we were talking about last time, we briefly started talking about making this move from prediction tasks, right, supervised learning, where we have some y that we're trying to predict from x, to somewhat more amorphous problems where we have a data set and we're trying to understand certain structural properties of that data set, right? And the example that we briefly talked about, one was the idea that we might have a bunch of images and we want to cluster them or group them into different sets that contain similar kinds of subjects or similar types of landscapes. Okay? Broadly speaking, when we're talking about clustering, right, we have this idea that we have a data set that belongs to some number of dimensions, and the goal of clustering is to find sort of groups of that data such that within a group, there's a lot of similarity of some sort between the data points relative to the similarity between points in different groups, right? So the way clustering generally proceeds is that the user or the person who's trying to find a clustering says how many clusters that they would like, right? And then the goal of the remainder of the process is to pick clusters, that number of clusters, to minimize an objective function. Okay? So that simply looks like choosing some collection of assignment of points to clusters in a way that minimizes some objective function, which is a function of the assignment and possibly, in some cases, as is in the case we'll talk about today, the centers of those clusters. K-means in particular is perhaps one of the most ubiquitous objective functions one might try to minimize for clustering. And what the K-means objective asks that we find a clustering to do is to minimize the average squared distance between any point and the center of its cluster. Okay? So we're going to assign points to clusters. Those clusters will have some centers, and we are asking to do that in such a way that the average squared distance between any point and the center of its cluster is minimized. So we asked last time, now that we're finally getting into some of the technical meat about this, how we ought to minimize this quantity, right? How would we actually find such an assignment of points to clusters and find the centers to minimize this objective in a computational sense? And we mentioned that, and this is going to be NP hard to minimize exactly for many data sets, but that there are several nice algorithms that behave well in practice. So we'll talk about one in particular, right? So if I gave you, you could try one of a couple things, right? One of which might be brute force, right? You might think about all possible assignments of points to clusters and sort of find the one that minimizes that objective, right? And that's certainly one thing you can do, right? The computational complexity of that is something like n to the k, where n is the number of data points and k is the number of clusters, right? And in the worst case, the algorithm I'm about to describe will have computational complexity somewhat similar to that, but it often works much, much better than doing something brute force like that in practice, meaning it converges to something that seems to have pretty low objective value for the Kmeans objective, and it seems to do so relatively quickly in a lot of instances. Okay, so this algorithm that I'm going to describe is known as Lloyd's algorithm, and Lloyd's algorithm operates as follows. Sorry, it's not clear why this is not working. Okay. Okay, so Lloyd's algorithm tries to minimize the K-means objective in a greedy way by first randomly selecting K centers, right? So this would be mu1, mu2, up to mu k, right? Starts with a random initial assignment. Then assigns each point in the data set to the cluster center it is closest to, right? So the drawing here is a nice one, right? That in the case of, the K-means objective, there will be some nice like convex sets that describe which points belong to which centers, right? Belong meaning find that center the closest to them. Okay, so we've randomly assigned some centers. We've then assigned points to belong to the cluster corresponding to the cluster center closest to them. Okay, what would be the natural thing to do next, right? We could stop there, or we could say there's a better set of centers for these particular clusters, right? If we fix the assignment of points to the clusters that we just described, the best center to minimize the objective is to find the center or the centroid of those clusters. Right? So rather than the initial random centers, right? This was maybe mu1, the initial mu1. We're going to move the centers of the clusters to the points, to the point which is actually the centroid of the points in that cluster. So once we've done that, it's no longer guaranteed to be the case that the points belonging to a cluster actually are in the right cluster anymore, right meaning belonging to the cluster for which they are closest to the center. So you can then do the same thing, right? You can say, okay, I have new cluster centers. I'm going to reassign points to clusters defined by those new centers according to whichever center is closest to them. We'll then induce a new centroid for those new assignments, which would then induce new closest centers for all of the points, right? So you can randomly guess centers, assign points to centers, recompute centers, recompute the closest center for every given point, and repeat this process continuously, right? So this is basically going back and forth between updating the centers to be actually the centroids of the points belonging to that cluster, and updating the assignment of points to clusters based on the new locations of the centers. So, slightly more mathematically, that just looks like this, right? Assign the point I to the cluster. Oh, this should be, yeah. Assign the point xj to the cluster I which has the closest center, and then so actually define the new center as a function of the points belonging to that cluster. Is the description of the algorithm clear? Does anybody have any questions about how, this is a very greedy process, right? It's like fix the centers, assign the points to the clusters, which minimize the objective function as though those were the true centers we are going to end with, and then sort of fix the assignment of points to clusters and change the centers to minimize the objective as much as possible. Questions about that? Okay. So it's natural to ask how well this algorithm may behave, right? And at least at first blush, it's not even clear whether this algorithm will converge or whether it might cycle, right? Because we're basically doing this back and forth where we're updating the centers, we're updating the cluster assignments. Where's the guarantee that this won't sort of run forever? Okay, so as I was describing a moment ago, the way this, geez, I don't know what this is. Okay, the way this algorithm behaves is it first fixes centers, and then it minimizes the objective function by manipulating the assignment of points to clusters. It then fixes the assignment of points to clusters and minimizes this objective with respect to the centers. And what that means is our objective value, this K-means objective, decreases each time we take a step, right? Because if we fix mu and we minimize with respect to C, that's only going to decrease our objective value. If we fix C and we minimize with respect to mu, that also only decreases our objective value. So that's a really nice way to convince ourselves that the algorithm won't cycle, right? Because for the algorithm to cycle, we need the objective value to be the same at two different points. That means that we won't see any assignment of points to clusters that are exactly the same with the same centers twice. So the number of unique assignments of points to clusters is roughly n choose k, many ways to assign points to clusters, which is of order roughly n to the k. And that means that this will converge in a finite but possibly very large number of iterations back and forth between updating the centers and the assignments. Good. Okay, so n to the k isn't exactly awesome worst case runtime for an algorithm if n or k are even modestly large. However, in practice, we see that this often converges much faster than that. It's also not totally obvious that this would converge to the global optimum. But it's worth thinking about those things, and we'll have you think about some of those things on your homework. Okay. So one thing that's kind of neat about K-means is you can actually use it as a way to compress a data set. So I'll just talk about this really briefly, but you can imagine the following, right? So you can imagine you have an image and you can divide that image up into smaller pieces, right? Relatively small pieces. And then you can, each of those patches of an image, you could think of as a data point. Right? If you think of each of those as a data point, and then you cluster your patches using K-means, you suddenly have, for the number of clusters you have, can now be used as a way to compress your image by saying, rather than treating each patch as sort of as its original representation, you can just say that you're going to treat a patch as the center of the cluster that patch was assigned to in Kmeans. Okay? Which means all you would have to store for an image, rather than if you chose to compress an image in this way, are the K centers that you found when doing K-means. And then for each of the patches in your original image, you don't actually have to store the entire patch. You just have to store a number between 1 and K, which takes at most log K bits, corresponding to which of the centers you're using to represent the patch of your image. And this is just like a nice image of using that technique. Okay. So you might want to know when you actually want to use K-means versus some other kind of objective function for doing clustering, right? If you know that you have some data set, that you want to find some meaningful pieces of mass of the data within it, when might we want to use K-means, and when might we want to use some other kind of objective function? And the short answer is, it depends on what kinds of groupings you're trying to find, right? If you have a really nice data set that has sort of well-separated clouds of data points that have similar diameters and similar shapes, and those shapes are reasonably round, right? These are great examples of, like, these are clusters that K-means is quite likely to recover, right? Meaning, like, minimizing the K-means objective will correspond to finding these groupings, right? On the other hand, if you have a data set where you're looking to find clusterings that don't look like this, right? For example, if you suspect your clusters might be overlapping, or if your clusters may have very different widths, the clusters you might want to find might have very different widths, or if they're not sort of round, then you might prefer a different objective function, right? And there are many other natural ones that have been studied quite extensively. We won't talk much about them. Perhaps towards the end of class, we'll come back and bring a few of these to the fore. But these are doing most of these other objective functions, they'll find different shaped clusters in a data set, but they have similar large goals, which is that they have some large, given a large data set, you want to find some segmentation of the data set into sort of like similar points within a clustering, and the definition of similar will be different for these different things. Okay, so one bad case for K-means, right, just to drive this point home, is the following image, right? If we actually believe that this is a cluster we want to uncover and this is another cluster, K-means is going to do a really poor job at this, right? And we may have you experiment with some of that going forward, but if you suspect that this is the way your data looks, and furthermore, this sort of smaller circle, this dense region, is a cluster you'd like to uncover independent of the larger set it lives within, K-means is not going to do that for you very well. Okay, and you can maybe do like a little bit of a back of the envelope calculation as to why that is. Right. So K-means is just a clustering objective. And Lloyd's algorithm is a greedy heuristic for minimizing it. It will, in general, converge in finite time, but it may not converge to the global minimum of the K-means objective. One other thing that's really useful to think about is whether sort of picking random initial centers is the right way to initialize Lloyd's algorithm. And the short answer is it's not the best way. There are better ways to pick centers. And there is, even in a theoretical sense, not just in a practical sense, there are better ways to initialize your centers than picking them uniformly at random from your data set. So if you're actually planning to implement Kmeans and not use like an off-the-shelf implementation, if you want to implement something that approximately minimizes the Kmeans objective, think about how you would seed that algorithm. Okay, so not to give anyone whiplash, but we are moving on to another topic. Now that we've given you sort of the world's shortest introduction to clustering. Okay.
And I just want to emphasize this seeding of the algorithm is really critically important. In many applications, if you run Kmeans, you will get out terrible clusters. But if you initialize with Kmeans++, it will just work wonderfully well. It's a shockingly simple algorithm, initialization, but it makes a huge world of difference in practice. And so, like, almost to the point that I would recommend never not using it. But it can be computationally intense to do, so sometimes we don't do it.
Yeah,
but you'll have some practice on the homework using it.
Yeah, it's right. So a careful initialization of your centers won't get over the hump of the fact that this problem is NP hard this objective is NP hard to minimize exactly. But a careful initialization can give you guarantees for the objective value that you'll get when you run Lloyd's algorithm with good initialization. So, it'll give you sort of an upper bound on how bad whatever solution you converge to might be, right? Which sort of with random initializations you don't get. All right, so we're now going to talk, at least for the next 20 minutes, about another set of techniques which are really integral to understanding data, where you don't have an explicit prediction goal in mind, right? This is another unsupervised learning technique. But instead, rather than trying to understand sort of groupings of your data, you now want to understand sort of the inherent dimensionality of your data, or sort of, if your data set is in many dimensions, how well you can represent that data in many fewer dimensions, right? And this is useful for all sorts of different applications, which we'll briefly touch on today, and we may talk about more on Monday. So the thing that we'll talk about for the remainder of lecture is the following thing. So given a data set, right, that belongs to, we have n data points that belong to RD. Is it possible to find a compressed representation with only Q dimensions rather than D dimensions, such that we can represent every point in our data set as a linear combination of those Q vectors? So this is just the average. The average vector from X. Okay. So finding, the goal of much of dimensionality reduction is just to find a way to represent data that originally lived in D dimensions, finding a representation of it in Q much less than D space. Okay. So PCA is one way to do that, right? PCA stands for Principal Component Analysis, and we'll talk more about the specifics of that in a minute. But data-dependent dimensionality reduction is the name of the game for what we're talking about for the rest of the lecture, right? The idea is we're not just going to sort of take our data set and project it onto the first dimension, the first feature we have, ignoring everything else. We're actually going to look at something structurally integral about the specific data set we have and find a meaningful way to represent that data in fewer dimensions. Right? And the way we're going to do that is going to depend on the particular data set we have, not the algorithm that we use, but sort of the reduced space, and the projection we're going to look at is actually going to be a function of the data set itself. And finding lower dimensional representations of our data sets there are many, many good uses of such things, right? For one, humans are super bad at visualizing high dimensional data, and we can't, draw on our screen something that's more than, say, 3 dimensions, maybe 4 if we use colors, right? So, if we have a really high dimensional data set, one way we can help visualize it is by finding a lower dimensional representation and drawing that. It's also useful for sort of understanding correlations, right? When we have many features, it's easier to look at some much smaller subset of those, or some much more, It's also the case that if you have a high dimensional data set, one of the things you'll find if and when you are operating with a high dimensional, possibly many road data set, is that actually doing computation and storing such a data set can be really, really computationally and memory inefficient with respect to computation and memory. So if you actually think about finding a low dimensional representation, you can actually carry that around with you everywhere and compute with respect to it and store it in memory rather than your original higher dimensional representation. And finally, finding low dimensional representations, suppose you have a 100-dimensional data set and you find a 3-dimensional representation, and you actually convince yourself that that contains virtually all the same information as your original 100-dimensional data set. Well, that also tells you something about the data set you initially were considering, namely that there may be some much lower intrinsic dimension to your data set than the 100-dimensional space it initially lived in. And Kevin alluded to this, I think it was in the last lecture or perhaps the one before, where he was talking about points lying, maybe the points live in a 100-dimensional space, but really they sort of lie on a nice plane or a nice manifold or something, right? Dimensionality reduction can help you sort of uncover the fact that points may live in a much lower dimensional space than they're currently embedded in. Okay, so I want to briefly walk through a kind of fun example, right? Which is the following, right? So suppose we have a collection of people who have preferences over different kinds of food, and they've ranked these different foods from 1 to 10, which represents how much they like these different kinds of food, right? So Alice, Bob, Carolyn, and Dave are specific x1 through xn, right? They are the data points in our data set. And this is feature 1 to feature n. Right? And the claim that we'll make is that we can actually represent this data set using less information than we currently have here. So if we look at the average amount that people like kale in this data set, this is a data set that was comprised on the West Coast. The average preference for kale is above 1/2. The average preference for Taco Bell is 4.5. The average preference for sashimi is 5, and Pop-Tarts is 5.5. So kale and Pop-Tarts equally desirable in this example. Okay. So the goal of dimensionality reduction is to find a way to describe each of our individuals' preferences as a combination of the average preference for all of those different foods plus some linear combination of 2 standard vectors that we'll find. So a simple exercise that you can do is convince yourself that you can actually describe everyone's preferences in this table using these 2 vectors and the appropriate linear coefficients. So what this means is that, like, while this data set initially had 4 dimensions, we can do a really nice job, in fact, I think in this case, a perfect job, representing everyone's preferences using only 2 vectors and linear combinations of those 2 vectors, right? Every one of our data points in our data set is describable as a sum of the average value plus some linear combination of these two fixed vectors. So in general, it won't be possible to do that, right? It won't be possible to find a perfect representation of our data in many fewer dimensions than it initially lives. But we might want to understand the best representation we can find of our data set in fewer dimensions. So for the first example we might want to work through is thinking about, okay, we have initially a d-dimensional data set, and we want to find sort of one dimension. If we're only allowed one dimension, what's the best dimension that we can use to represent as much of the saliency of the data set we have as possible? Okay. So we want to choose, you know, if we're thinking about like going from 2 dimensions to 1 dimension, the picture is relatively nice. We have a bunch of data points, right? These are just belonging to x. Right? This is x1 and this is xn. We just want to find a line in space such that when we find the distance between the points that we're considering in that line, that average distance is minimized. Right? So if we do that, what that means is that this line, if we project all the points onto this line, that's now a 1-dimensional representation of our previously 2-dimensional data set. And furthermore, we've sort of moved the points as little as we could, right, while representing them all in 1 dimension. So I've sort of alluded to this idea that we're doing sort of 2 things simultaneously, one of which is that we're minimizing the squared distance that we're requiring our points to move to represent them in 1 dimension. The other of which is that our data set had a lot of variance, right? Our initial data set, there was, you know, a fair bit of spread between our different points. Right? It's actually equivalent to find a line, rather than minimizing the sum of the square distances between all the points in that line, to instead think about when we project all of our data points onto this line, maximizing the variance of the points on that line. So these are 2 useful descriptions that turn out to be equivalent, which we probably won't talk about much today, but comes out of some basic understanding of the optimization that we're going to be thinking about. So principal component analysis is just looking for a high fidelity linear projection from d dimensions into many fewer, in this case, q dimensions. Okay? So given a data set, what we want is to find a representation of that data set in q fewer than d dimensions, which minimizes, right? This is going to start to look, this is just minimizing the average squared distance from, you know, from the point to the place where we actually project it, right? So this is just looking at the projection of the point onto the, it's no longer going to be a line, right? If we're thinking about q being larger than 1, right? What we're actually looking for is a space, right? Of q dimension, of dimensionality q. Okay, so if we look at this optimization problem, right, that says what we want to do is we want to minimize over mu and this matrix BQ and these linear and these scalars lambda I. Sorry, these are not scalars; these are vectors. What we want to do is we want to find basically we want to find a matrix where we're going to project our data set down onto that matrix, and we want to minimize the average distance squared between any point and its projection. So if you fix this projection and we solve for mu and lambda I, those have really nice forms, right? Mu, as I mentioned before, is just going to be the average value of all the x's, right, in each of its coordinates, right? This is, again, a vector that lives in Rn. And lambda I is a vector that lives in Rd, right? Lambda I is simply describing the coefficients that we're going to place in front of each of the vectors that we're using to project xi, and it's saying how important each of those vectors is when doing our representation of xi. That means we can equivalently write this minimization problem as this one, right? And all I've done here is done, some basic substitution. And VQ transpose is called the projection matrix, which minimizes the error of this projection when thinking about finding a basis of size q. All right. So if you look at this optimization problem, right, this is the one we were just talking about before, we can make a definition that makes our lives much easier, which is to define sigma to be this particular matrix, right, the covariance matrix. And then if you do some substitution and some basic linear algebra, you can show that this is the same, right, that these two quantities are equal, right, that you can then instead think about the problem of finding your matrix BQ that minimizes this quantity here, right? Which, if you're wondering why finding a matrix which minimizes reconstruction error, or that distance between your point and its projection, why that's equivalent to maximizing the variance of the points once they're projected onto that space, think about the fact that this minimum, sigma, has nothing to do with VQ, right? So this is equivalent to minimizing the second term, the negative trace of V transpose Q sigma VQ, or maximizing this trace. Okay. So that's the perspective that will tell you why minimizing sort of the distance between your point and its projection is equivalent to maximizing the variance of the points once they're projected. So if you want to actually solve this problem, right, you actually want to find the projection, or the sort of representation of all of the points in this lower Q-dimensional space that does the best job in terms of representing the variance in your data initially, it's useful to think about this fact, which we'll talk a little bit more about next time, but that the matrix which actually minimizes this quantity has the first Q eigenvectors of our covariance matrix as its rows. So we won't have a huge amount of time to talk about it today, but the intuition you should have here is that the first eigenvector of a data set, or of a covariance matrix, right, represents the direction in which there's the most variance of your data set, right? And that's not necessarily, a direction that is equal to one of your standard basis vectors, right? It may be, for example, if we look at this, if we look at this example right here, right, the direction of most variance is not equal to one of the directions of one of the features, right? It's some linear combination of those two, right? And we actually capture a lot of information about this two-dimensional data set just looking at that one So we'll talk more next time about what this connection between finding a lower dimensional representation of our data set in Q dimensions and actually computing the top Q eigenvectors for the covariance matrix of that data set, and sort of how computationally you might want to do that. I think I'll stop here just because we don't have time to do the remainder of the analysis for today, but we'll talk about that on Monday. And I'll stick around to answer questions and have more of a discussion. I'm actually going to try to stop the recording, if that's possible. Okay, I've stopped the recording for anyone who wants to stick around and ask questions or have a conversation about the first part of the lecture.
I have a question about this first Q eigenvectors. Like, what does this first Q mean? Like the ones with the highest eigenvalues?
Yes.
Oh, I have a question about the highest eigenvalues. Like, does that mean they have to be the highest in absolute value, or just like biggest in norm? Like,
so they will all be positive for the covariance matrix because it is symmetric, right? So yes, with respect to all of your questions, but the short answer is all the eigenvalues will be non-negative.
oh, okay.
Right, so if you take the eigenvectors of a positive semi-definite matrix, which this one will be, then the eigenvalues corresponding to those eigenvectors will be non-negative.
It is easy to see by if you, like, what is an eigenvalue for a matrix A? An eigenvalue vector pair of like lambda V satisfies AV is equal to lambda V. So that means V transpose AV is equal to lambda times V transpose V, which we're assuming is 1. And so the eigenvalue itself for a corresponding vector V would be V transpose AV for some vector V. Now, if you look at that sigma covariance matrix on the slide that Jamie has here on the bottom right, if you hit both sides of that by V transpose sigma V, you'll get V transpose Xi minus X bar. And then again, you get Xi minus X bar transpose V. But those two things together is just quantity V transpose Xi minus X bar squared. And so, which is a proof that the eigenvalue has to be non-negative. Or it's a proof that basically this matrix is positive semi-definite. Which means that all of its eigenvalues are positive or non-negative. And so this interpretation Jamie's talking about is basically saying that you're searching around directions V such that you're getting the first principal component is looking in the direction with the most variance. And so you're sort of thinking of sweeping around V until it's getting the largest possible eigenvalue. That's the largest amount of energy projected down onto that component. And then once you find the first one, you look in directions orthogonal to that original direction and try to maximize again. And you just repeat this process iteratively. That's one possible algorithm. SVD does not do that, but intuitively, that's what's going on.
Other thoughts, questions?
I had a question about K-means. So for a set of data points, if I could give you like the distance between each point and every other point for all the points, could you solve that optimization problem like perfectly? Is it possible then, or is it still not possible?
Wait, say that again.
So for K-means, yeah. So if I give you the distance matrix, right, for the whole set of points, then can you solve that? Say you can compute that super efficiently, whatever. Can you solve that problem perfectly? You still can't?
Not in a guaranteed amount of time that is polynomial. No. So it's not that it's computationally super expensive to compute distances, right? That's like going to be like n squared d or something, right? Like where d is the dimensionality. Like that's just like not too slow. The real problem is this, like you're solving something that, like, depending upon which points belong to a given cluster, another point may or may not want to belong to that cluster. Right, so like the problem is that like there's interaction between points in a cluster and other points that are now close or will not be close to that cluster, depending upon if those other points move. Right, if you're thinking of this as an iterative process.
Right.
Yeah, I mean, the tricky part about Lloyd's algorithm, and it's kind of a great example of a pattern that comes up a lot, is if you fix the centers, finding the clusters is very easy. And it's closed form, and it's very efficient. And you fix the clusters, and then you solve for the means. That's also a convex problem, very efficient. But when you do, so what we call this is a biconvex problem, or it's related to a biconvex problem, where if you're doing this alternating minimization, each step of the alternating process is very efficient and perhaps convex. But when you put them together, the full problem in together is non-convex. And so if you're doing convex optimization with a gradient descent, if you have a function f of x, y equal to x times y, if you fix the value of y and minimize x, that's convex. If you fix the value of x and minimize y, that's convex. But x times y is not convex.
Right. Got you. Interesting.
Yeah, and I mean, there are cases, so like one of the reasons people use this in practice, use Lloyd's algorithm and use the Kmeans objective in practice, is like, if your data is really nicely clustered, right? If the Kmeans objective for the minimum is actually quite small, or if, there are a variety of conditions under which we actually do know that this sort of iterative process is guaranteed to converge more quickly. But that's only basically if like something like Lloyd's algorithm is relatively stable, right? That relatively few points move in any given iteration.
Got you. Thanks.
There's some really beautiful like papers in the last, and Lloyd's algorithm and clustering in general, super old, but like in the last 10 years or so, there's been some nice development in terms of like when you can guarantee it'll converge more quickly and to the global